And then we pour, if I would like to have a little bit of grape juice. And then we pour the rest to put out the candle. And then we will sing a song about Elijah the prophet. We also sing at Passover and other transitional times in our lives. Eliyahu Hanavi, Eliyahu Hatishbi, Eliyahu, Eliyahu, Eliyahu Agiladi, Bimera v'yaminu, Yavo Elenu, Mashiach ben David, Mashiach ben David. And now we wish each other a good week, a Shavua Tov.
Shavua Tov.
Shavua Tov, 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 Shavua Tov. A good week, a week of peace. May gladness reign and joy increase. A good week, a week of peace. May gladness reign and joy increase. Shavua Tov.
Shavua Tov.
So I'd like to announce, thank you. I want to say thank you to Aaron Kraft and thank you to Ephraim for your help with Havdallah. I'd like to introduce Professor Josh Wynn. He used to be an astrophysicist at MIT, and he's been at Princeton for the last, how many years? 4 years? 5 years?
5 years, yeah.
5 years? Okay. In full disclosure, he is my cousin-in-law, and I'm very thankful that he is. And last year when I proposed this Space Havdallah idea for him, he's like, why are you doing this? And I said, it's because actually, before we recite Havdallah, we're supposed to see 3 stars in the sky. When we can even like run outside and go see if there are 3 stars and if it's time to say Havdallah. So Judaism is very rooted in like the natural world and paying attention to the natural world. So with that, I am very excited to introduce Josh Wynn. Thank you for being here. And would you like me to spotlight you, or do you just want to?
Whatever.
I'll spotlight you for now, and then when we have questions later, I'll unspotlight you. How about that?
Okay.
You should turn your volume.
I'm now going to try to show you some slides. So how does this look, Elise? Do I need to switch?
It looks good.
Oh, okay, good. So, as Elise just said, this is not just Havdallah, this is Space Havdallah, when we connect our rituals with the natural world. And there's actually a lot of exciting news in the world of astronomy and astrophysics these days. So I'm very happy to be here and share it with you. A lot of the most exciting news is related to this thing. Does anybody know what this thing is called? I know you know, Ephraim. Let's see if anybody knows who's joined us today. Anyone know? Feel free to just call it out if you happen to know. All right, Ephraim, over to you. What is it?
It's the James Webb Telescope. It's like the new.
That's right. This is our newest toy in astronomy. It's called the James Webb Space Telescope, and it was launched into space on a rocket on December 25th, so not so long ago. And starting this summer, it's going to start making all kinds of interesting astronomical discoveries. So what I want to share with you tonight is, what is this thing? Why did we need it? What does it do? Why does it look the way that it does? It doesn't look like an ordinary telescope. So hopefully with some of the pictures I'm going to show you and some of your questions I'll try to answer, you'll have a better understanding of what's going on. Let's see, Edward, do you have a question to start us off?
I have 2 questions.
Sure.
One question is A, do you know Elon Musk? And B, do you think like when do you think humans would be able to like live on another planet and like not die out after maybe like a year or a couple months?
Yeah. Well, so you have two questions. They're both great questions. I'll answer the easy one now, and then we'll come back to the harder one afterwards, after we talk about the telescope. So the easy one is your first question. No, I'm afraid I don't know Elon Musk, although he seems like he would be a very interesting person to get to know. And as for your question about whether people might live on other planets or whether other planets are inhabited, that is such a good question. It's a deep
Like,
question.
how long do you think that would take? Like,
All right.
let's say like the world, humans need an escape from this world, from like this planet.
Yeah, I hope we're never in that situation, but hold that
In
thought.
like 100, like 50, 100 years or so, or maybe more. Like, do you think we'd be able to escape by that time?
Let me return to that question later. So back to our telescope here. Let me ask a more general question about telescopes. Why do we have them at all? Why don't we just look up at the sky with our eyes like our ancient ancestors did? Why isn't that enough to make discoveries about stars and planets and galaxies? It's actually a subtle question. A lot of people think we need telescopes to make things look bigger, to magnify things, to make it look like they are closer than they actually are. And that is true. That is one reason why people use telescopes, but it's not really why astronomers use telescopes. If you are a sailor and you want to see some ship that's far away on the ocean, you would use a telescope to make that other ship look like it's closer. But in astronomy, that is not the main reason we use telescopes. So let me explain what the main reason is, and I'll do that by way of a picture. What is this thing? What kind of creature is this?
It's an owl.
Yeah, and what is special about this picture of an owl? What is so striking about it?
Eyes are big.
Its eyes are huge, yeah. Let me show you another picture. What is this thing? I'll bet you've never seen one of these before. Ephraim, what is this thing?
It's a lemur.
It looks like a lemur.
It's
That is
a
a very good guess.
It's a bush baby.
I don't think it's a bush baby. This is an animal called a tarsier.
Oh,
It lives in Southeast Asia, on the Philippines and other areas there. Even though you may never have heard of this animal, let alone seen it, I'll bet you can tell me something about this animal just from this picture. What can you tell me about the way this animal lives? Eyes are huge, right? Why would it need such huge eyes like the owl?
Is it nocturnal?
It's nocturnal.
That's right. This is a creature like the owl that is most active at night. And at night, there is not much light. And so if you're going to get around at nighttime and either find your prey like the owl or avoid your predators like the tarsier, you better make the most of any of the faint light that does exist at night. And that's why these creatures need big eyes, because these big openings in their head let in more light than smaller openings would. And for the same reason, astronomers work at night, right? We work in the nighttime. There's not much light coming to us from distant stars and planets and galaxies. And so we need bigger eyes to take maximum advantage of that tiny amount of light that does exist at night, like this person is doing. When you're looking through a telescope or a pair of binoculars, you are effectively enlarging the size of your eyes. It's as though you had eyeballs that are as big as the openings of the telescopes, just like an owl or a tarsier, or even much bigger. Now, you don't actually have to have two telescopes like this person does in this picture. It's usually enough just to have one telescope and look through it with one eye in order to study the objects that we see in the sky. And these days, we don't even look with our eyes, to be honest. We hook up our telescopes to cameras and computers, and then we record the image that is seen through the telescope on the computer so that we can study it and make all kinds of measurements. And because the digital cameras that we have now are actually much better at detecting light in some ways than our eyes are. So it's another way that we improve on our eyes. We enlarge them by having a very big telescope, and we use a better detector than the retina in the back of our eyes. We use digital cameras, and both of those things help a lot. So when you do look out at the sky at night with just your eyes, without any telescope or binoculars, you see a lot of stars. At least I hope you do if you're in a relatively dark part of the world. And you might also see a smudge. Can you see my arrow here, Elise? Okay, good. You might see an occasional smudge in the sky like this one. This is called the Andromeda Galaxy. It is the most distant thing you can see without using a telescope, with just your eyes. But honestly, it doesn't look like very much. You can barely make it out, and it looks just like the faintest little piece of fuzz out there among the stars. And with a small telescope, this is the view that your camera might make of this object, the Andromeda Galaxy. So you can tell that there's something there. There's something kind of whitish that stands out against the static, but you can't make out much detail. But if you take the picture of an Andromeda Galaxy with a larger telescope, bigger opening, you can see more detail. You start to see the galaxy as this elliptical blob here. And there's another little galaxy down here that we couldn't see very clearly before. And if you make the telescope even bigger and bigger, now you start seeing what's really going on. This is a galaxy that has these swirling lanes of stars, and dark lanes and bright lanes, and there's lots of stars in the foreground as well. So I hope this shows you why we want telescopes and why we want them to be huge. The James Webb Space Telescope is almost certainly larger than the room you are now sitting in. Its main mirror is about 25 or 30 feet across. So it's enormous. And it's like enlarging our eyes to be that same size, as large as a large room. Let's see, I see there's a question from the Barron family. Maybe? Okay, well, I will go on. I want to show you some of my favorite pictures, just kind of randomly selected, that we can, the kind of detail that we can only see when we have a huge telescope. So this is an interesting
The question came in chat. Put the question.
Okay. In the first picture, what were the purple dots? Is that this one, maybe? I'm not sure if this was the picture. Okay, I see a thumbs up. Yeah, so these are all stars. All of these dots in the sky you see are stars. And stars do have different colors. If you're very observant and you're in a very dark location, you can tell that some stars look a little bluer than others. Some stars look a little bit redder. And so the purplish looking dots you're seeing in this image are, in fact, purple colored stars. They're relatively blue compared to the average star. And in this image, the way that the photographer or artist decided to process the image, that really emphasizes that purple color. So here is an arresting image of a young star cluster. So all of these stars in this part of the image, those are young stars. That means that they're only a few million years old. The sun is 5,000 million years old, or 5 billion years old. These stars might be only 5 million years old. So by astronomical standards, these are baby stars. And this material that you see around it that's glowing, that is the original cloud of material that collapses in order to make new stars. So these stars formed from a cloud of gas and dust that looked just like the glowing one that we can still see in this image. This is another interesting site. This is not a young star cluster. This is actually a dead star as opposed to a very young star. This is a star that exploded. It's called the Crab Nebula, and it exploded in the year 1054. And the reason we know that is because the ancient Chinese astronomers saw it and they wrote it down in their logbooks at that time. New star appears in the sky, very strange. And so we know exactly when this thing exploded, and it has been fading away ever since. And this is an entire galaxy of stars. So it looks almost like a flower, doesn't it? It's very beautiful and delicate, but it is actually composed of hundreds of billions of stars, each of which is as powerful as the sun. But there's so many of them, and they're all so close together that they just form what looks like a fluid, like a milk made out of stars. And just like the galaxy that we are in, the Milky Way, this is a galaxy that goes by the name NGC 1398. There are so many of these beautiful, interesting galaxies that they don't all have names, really. They just go by catalog numbers. That's how full the universe is of these wonderful things. Okay, so the first reason we like our telescopes and we like them big is because they help us see fine detail of things that are very, very faint by collecting more light. Now there's the second reason, and it's one that's a little harder to understand, but very important for understanding the James Webb Space Telescope. And that is because we like to split up the light into lots of colors. Maybe at some point you've played with a prism, a piece of glass, and you send a beam of light through that piece of glass and it spreads out into a rainbow. Well, we can do that with starlight too. We can put a prism inside the telescope, spread out the starlight into a rainbow, and then take a picture of that rainbow. And the reason we do that is it teaches us a lot about what the star is made of, about the temperature of the star, about how much power the star is putting out into space, and about what is it composed of, what kind of elements are in that star's atmosphere. We can study all of those things by looking carefully at the entire rainbow of the star's light. But we can actually do even more than that. So this is what a rainbow looks like. This is what it would look like if you took sunlight, sent it through a prism, and spread it out into a rainbow. Meanwhile, though, question, Ben?
Is there a lot of variation in the elements that make up a star's atmosphere from star to star?
Well, to first approximation, no. If you just want to know what is a star made of, the correct answer is it is about 3/4 hydrogen, 1/4 helium. That's the recipe in general. But if you want to know about the details, it's actually, there are a couple of percent other things. It's really 3/4 hydrogen, maybe 24% helium, and 1% everything else. And that includes carbon, oxygen, nitrogen, it includes iron and all the metals and that kind of thing. All of that is included in the 1%. And that does vary from star to star. Some stars have 1%, some stars have 3%, some stars have 0.5%. So that is the thing that varies from star to star. Okay, so this is the visible light. This is what we can see with our eyes if we were to send light through a prism, send sunlight through a prism. And this is what an ordinary camera would see as well. But one thing we've learned, a really amazing thing that we have learned over the last few hundred years, is that our eyes are not perfect. And there is a lot of other types of radiation besides light that is all around us that we are blind to. And the visible light is just a tiny slice of this much larger concept called the electromagnetic spectrum. So we see only a tiny slice of what is really a huge range of types of radiation, going from gamma rays to X-rays, ultraviolet, infrared, microwaves, radio waves. If you've heard those words, you probably didn't think they had anything to do with light, but in fact, they are all related. we've given different parts different names, but that's artificial. Really, it's just one thing. And what is varying as you go from one end to the other of this chart is the energy of the radiation. So visible light has a kind of a medium energy. If you pack a lot of energy into the radiation, you might get X-rays or gamma rays. And if there's hardly any energy in each little bundle of light, then it's more like microwaves or radio waves. And our eyes are only tuned to be able to see this tiny little slice of it. It is as if there were a piano with 88 keys, but we could only hear 2 of them or 3 of them. We would be missing out on so much of the possible music that one could play. Likewise, there is so much that we would like to observe, but our eyes are simply not sensitive to it. Now, you've probably heard of ultraviolet and infrared radiation, if you're into science at all, at least. You might even know that some insects can see ultraviolet light. So when we look at a sunflower, this is what we see. But when an insect that can see ultraviolet light looks at the flower, it probably sees something more like this. A lot of flowers have pigments in them that are not meant for us. They are only meant for the insects that pollinate them, and they only really produce contrast in the ultraviolet range of this spectrum. By the way, this is called a false color image. If you ask, what would it be like to be a bee with ultraviolet vision? We can't tell you. We don't know what it looks like because we can't see ultraviolet radiation. But we can detect it. We can build cameras, special cameras that can detect ultraviolet. And then we can use the information from those cameras to shift the energies down and show us what it would look like if it were visible light instead of ultraviolet. The same kind of patterns of light and dark that we can see, but that really only the bee can see with ultraviolet vision. Now, another type of radiation, and this is the one that the Webb telescope specializes in, is the infrared. But first we have a question. Elise.
What would that flower look like in infrared?
I don't have a picture of it. My guess is it would look not kind of bland. And that's because insects, for reasons I don't understand, I don't know why insects can see ultraviolet and we cannot. I don't know what advantage it gives them, but it is a fact that the pollinators of flowers can see visible and ultraviolet, but not infrared. There are creatures who specialize in infrared. They're the ones mainly who try to hunt by sensing the heat of their prey. And infrared radiation comes from hot sources like warm-blooded animals. So there are probably some things in nature that would be interesting to see in the infrared, but flowers are not among them. So one thing infrared is really good at is cutting through haze. If you see a fog or a haze of dust particles and you want to see through it, your best bet is to use an infrared camera. So this is the view from an airplane down at a scene, and it's kind of hard to see because it's a hazy day, but there's a river that is following my arrow here back and forth and back and forth. You can make it out now that I've pointed it out to you. But the same photographer immediately switched to an infrared camera and took a picture right after this. And it looks like this. The water looks black because the water absorbs infrared radiation. So it looks dark to someone with infrared vision. And the haze is basically gone. You can see right through the haze. And so it's much easier to see the river. So there are some things that we would like to study that are best studied with infrared light or with ultraviolet light rather than with visible light. And Webb specializes in infrared. So it's a huge telescope and it gives us an infrared view. So let me show you an example from astronomy now. This is that Andromeda galaxy again, the one that I was showing you earlier when I was talking about how the view gets better with bigger and bigger telescopes. This is what Andromeda looks like through an ordinary visual light telescope. Now, if we also look with an ultraviolet telescope, we get a different perspective. But jumping back to the visual, what we're seeing here is the combined light of many, many stars. We see there are a lot of stars here in the center where it looks kind of whitish yellow, and then it fades out as you go towards the perimeter. But at ultraviolet, most of the radiation is coming from the perimeter and not so much from the inside. And that's because of massive stars, really huge stars, 10 times the mass of the sun. Those kinds of stars emit most of their radiation as ultraviolet light. And what we learn from this series of images is that those massive stars tend to be on the outsides of galaxies, not towards the middle. We would have missed that if we didn't have an ultraviolet picture. If we look in the infrared, we see something else. When we're looking at the infrared, let me go back to the visible for a second. Do you see how there are these dark streaks in what otherwise look like a continuous bright light? Those are lanes of dust. Those are those clouds of dust that I showed you earlier in that picture of young stars. These are really spread out examples of those clouds that block the view that we have to things in the background. But as I said, in the infrared, we can cut through that kind of haze and see through them. And furthermore, we can see the dust itself is glowing. The dust is warm. And just as an animal with infrared vision would be able to see its warm prey in a forest at night, we can see the warm dust by tuning into the infrared part of the spectrum. So that's interesting. That's something we also would have missed if we didn't have this kind of picture. Here's an even better example of how we can see through dust with infrared. This is a dark cloud. So you see this black part where there are no stars. It's not because there are actually no stars. It's just that there's something in the foreground blocking our view, this big cloud. If we look at this, if we make an infrared picture of the same scene, we can see right through it. We can see the stars in the background. They're still a little bit darker than usual, but we have a much better view in the infrared. Okay, let me now skip a little bit. Okay, good. So I think I've answered our question. Why do we use telescopes? 3 big reasons. One is to collect more light, to be like the owl, to be like the tarsier. 2 is to separate the different colors that we receive from stars, to make little rainbows of starlight and analyze those rainbows and figure out what the stars are made of and how hot they are and so forth. And we can detect invisible radiation, like infrared radiation, that teaches us different things, interesting things about stars and galaxies. Now, finally, we come to the Webb telescope, and I want to try to explain why it looks the way it does and how it's going to work. So one thing you noticed about the Webb telescope is the mirror is strange. Most mirrors look silver, or they look like they're aluminum or gray or something, but the Webb mirrors they look gold. And they really are. They are coated with gold. There is a thin film of gold metal on top of the mirrors. And the reason that would be a strange way to make an ordinary telescope, because silver is actually much more reflective. But at infrared, in the infrared part of the spectrum, gold is a better reflector. And so if you're going to build a $10 billion telescope and you want it to have the most perfect technology possible, you don't mind spending some money and coating it with gold, because it's a little bit better than silver or aluminum or any other type of metal. So that's why it looks gold. Next thing you notice is that it's kind of a weird shape. It looks like a honeycomb, doesn't it? It has all these hexagons. Most of the time when you want to make a mirror, you would just want to make one big chunk of material. So why did they decide to make it in the shape of these hexagons and then glue the hexagons together to make a bigger hexagon? That's for a very practical reason, that we wanted the biggest possible telescope. We wanted a telescope 25, 30 feet across, but we have no rocket that is big enough to put such a telescope inside. Even our largest rockets, it wouldn't fit. So the solution that the engineers came up with was to build a telescope that could fold up into a tighter shape, to make it modular, to make the mirror come apart at the hinges so that it could be folded and then unfolded once it reached space. So it could be packed up tight for the trip to space in the rocket. So here is another picture that shows that even more clearly. Here, the mirror has been folded back on this side and on this side. So instead of seeing the full hexagon, the sides of the hexagon have been folded backwards, so you can't even really see them. They're out of view here. And that allows this to be a more compact, tighter arrangement that fits on the rocket. This picture is also cool because you can see these giant silvery things that are draped below the telescope. Those are also very important and were very difficult to engineer. Those are the sun shields. If you want to see infrared radiation, you want to keep your telescope and your camera as cold as possible. Because if it's warm, the telescope will emit its own infrared radiation, and that will interfere with your ability to see the much fainter sources of infrared radiation in the sky. So you need to make your telescope as cold as possible, which means that you need to shield it from the sun. You don't want sunlight to be falling onto the telescope, heating it up. So that's why the engineers went to all of this trouble to create these multiple layers of shielding from the heat and the light of the sun. By the way, I should have pointed out earlier, you can see there are some people here for scale. This is an enormous telescope, okay? This is huge. That's why it costs so much. Here it is all folded up and getting ready to be launched into space. So the mirror has been folded, and all of those sheets of mylar, or probably something much fancier, that silvery material has also been retracted and folded up and tightly bound to the outside so that it all fits into the cone, the nose cone of a rocket. Here is the liftoff itself. This, as I mentioned earlier, was launched on December 25th of last year from a launching pad in French Guiana in the northern coast of South America. That's where the European Space Agency has their rocket launching site. Now, I can't show you any pictures of the telescope right now, and that's because it doesn't have any webcams or anything on it that would allow us to see it. All we have is the data that we're receiving from the antenna from the telescope. We don't actually have pictures of the telescope now that it has arrived in space, but I can show you a video put together by the engineers that showed us what the telescope had to do to unfold itself once it got into space. And that's pretty cool to see. So here it is. So this is what the telescope probably looked like. This is a simulation of what the telescope probably looked like once it arrived into space. It's all folded up, and it's going to have to somehow unfurl. So here's how it works. And all of this was done successfully, by the way. So first, it extended its solar panels. That's how it gets energy, just to charge its batteries and keep all of the parts running. And then it started to deploy the sun shields. So it has to lower these panels and then stretch out that material to make these tennis court sized sheets that protect it from the sunlight and the sun's heat. So here they go. After another few seconds, it's going to start releasing. Now it's opening the cover for the sun shield and extending the booms that will support the sun shield. And there goes that material sliding outwards on one side. All of this took place over several weeks following the launch. There goes the other part of the sun shield. Now we still have to put the mirror back together. Okay, the sun shield is now in position. All those different layers. That's the secondary mirror. I have not explained what that is. I will do so in a moment. First, we have to unfold the main mirror. There we go. Putting all those hexagons back together. And there we have it, the Webb telescope. So what is this thing doing here dangling in the front? That's called the secondary mirror. And the reason it's there is because the purpose of this mirror, the big giant gold mirror, is to take light from some distant star, say, and focus it in one area, in one little part of space. And that's where you put your camera. You focus the starlight right on your camera. Now, the mirror by itself would focus the light right here in front of it. It bounces off of the mirror and then goes back outward and focuses it in front of the telescope. But this would be a pretty bad place to put a giant camera with all of the parts that are needed to keep it working well. It would be too big. It would end up blocking the view of the telescope if you hung the camera in front of it. So instead, what you do is you put a small mirror here that receives the light from the primary mirror and then bounces it back through a hole in the primary mirror. And then on the back of the mirror, that's where you put your big giant camera. So that's why there are two mirrors. The first mirror bounces the light and collects the light, focuses it on the secondary mirror, which then bounces it through a hole in the primary mirror and back to your cameras. So that's the Webb telescope. The other interesting thing about it is where it is located. It is not orbiting the Earth. It's in a very interesting orbit. It's more distant from the sun than the Earth. It's several times more distant than the moon is. So if you take the distance between the Earth and the moon, and you go away from the sun 3 or 4 times that distance, that's where the Webb telescope is. Now, usually, if you put something farther away from the sun, it orbits more slowly than the Earth would. And that would cause it to drift away from the Earth over time. If the Webb telescope were moving more slowly than the Earth, then eventually the Earth would move ahead of it and the telescope would fall behind, and it would be very difficult to communicate with the telescope if it were that far away. So what Webb does is it takes advantage of this mathematical fact that if you put the telescope in just the right place, so that it's just the right distance from the Earth, but on the other side of the sun, then the combined gravity of the sun and the Earth can cause the telescope to move at the same speed as the Earth does itself. So it can keep pace with the Earth when it's in this special orbit. In fact, it's even a little more interesting than that. It's going in a loop, which is itself going around the sun, as you can see in this animation. And the reason that was chosen is because it's nice and far away from the Earth. It's reasonably far away from the Earth. That means it won't be getting any stray light from the Earth that might ruin the measurements. And yet it's not so far away that it would be difficult to communicate with. And we can get back lots of pictures and lots of data. All right, now it's time for some questions. So questions, any questions about the Webb telescope before we venture into other things? Let me just take a moment to put my screen back the way it was. Okay, questions. I see a question from my aunt. Yes.
I was curious whether you had anything to do in creating this Webb telescope.
No, they don't. It's really a job for the engineers. The technology that's involved here is so sophisticated that it takes some of the best optical and mechanical and electrical engineers in the world to put something together like this. The role of the astronomers like me is to motivate the telescope, to tell them we need it to be this big because we want to be able to do this kind of project. We want to be able to see a galaxy that's this far away. We kind of give them a wish list, and then they figure out how to actually do it and get it into space.
So did they fulfill your wish list?
Well, we would always like it to be bigger, right? But yeah, I would. This is going to be a major advance over what we currently have. Our current best telescope in space is the Hubble Space Telescope. The Webb telescope will be better in essentially every way. It'll be able to see farther, see fainter things. It works much better at infrared wavelengths. There is one way, though, in which it's not as good. Honestly, though, Hubble can see ultraviolet, and Webb cannot. So that was just a choice that had to be made. You can't have everything you want for a certain cost, and so they decided to just have Webb specialize in infrared. And hopefully Hubble will keep lasting a while so we can still keep seeing ultraviolet.
Josh,
Yeah.
how does the telescope that you were working on fit into this program?
Yes. So I am part of a different NASA mission that's called TESS. It stands for the Transiting Exoplanet Survey Satellite. It's actually a spacecraft that has 4 telescopes on it, but they're little telescopes. They're much smaller. They're telescopes maybe so the opening is about this big. And there's 4 of them. and it works at visible wavelengths. It's not at all like Webb. Webb is a telescope that can be used for a million different things by lots of astronomers who are trying to answer different questions. The telescope I work on has really one purpose, which is to find planets. It looks for planets orbiting other stars by monitoring the brightnesses of those stars and looking for little eclipses if the planets go in front of the stars. So it's a very special purpose kind of telescope as opposed to Webb, which is a more general purpose telescope. So TESS finds the planets, and then we might use Webb to study those planets in great detail. I see there's a question from the Sobel family.
Go.
Well, I have a question. Is the multiverse real?
Right. So that is, so what is the multiverse? This is getting beyond Webb now, just for those of you who want to make sure they're following. The universe, the word universe kind of means everything that there is. So it seems a little strange to consider that there might be more than the universe. If the universe is everything there is, well, how can there be something bigger? And yet there are a lot of scientists who have begun speculating about the possibility that there are other universes that we cannot observe directly. That maybe there's millions of them. Maybe there's an infinite number of universes. And that concept is called the multiverse. Is it real? We certainly don't have any evidence at the moment that there is anything like that. As far as we can tell, there is one and only one universe. You know, there doesn't seem to be any way that we can access these other universes. The scientists who propose this do have reasons for these speculations. They're not just coming out of nowhere. They are inspired by some of our best theories for the fundamental rules of the universe, the laws of physics. But they are very much just speculation. They remain, it's more like it's not quite science fiction because there is some science behind them, but it may or may not actually exist.
He's got another question too. Do you want to ask your second?
Sure, yeah.
Does the black hole like go through time, and also is it like a portal, or does it like kill you?
It basically kills you as far as we can tell. Yeah. So a black hole is what happens when gravity is unopposed. There's nothing to fight gravity. And so a mass will just collapse like a star and form a single point that is just pure mass and nothing else, and has incredibly strong gravity if you get very close to it. So that is a black hole. And that is not like the multiverse. Black holes are real. They are not science fiction. There are places in the sky you can point and say, there is a black hole in that direction at this distance. And we're as certain as it's possible to be in astronomy about the reality of those black holes. But you ask a different question. You ask, what would happen if you actually visited a black hole? And there we don't really know, because all of our understanding of gravity is based on experiments we do on the Earth and about things we can see with telescopes. Gravity is so strong near a black hole that we might be wrong. We might not know the rules of how gravity behaves. So the honest answer to your question is we don't know. However, if you do take our understanding seriously, if you assume that we do know we know everything about gravity, then you would simply be crushed. You would become part of the black hole. You wouldn't jump into any other dimension or pop out somewhere else in the universe. That too is, for the moment at least, science fiction. The Barron family? Oh, how about Ben?
How long does it take to transmit information from the telescope to those that are monitoring it?
That's a good question. I happen to remember it takes on the order of a few seconds to get back from the moon at the speed of light. So this must be like 10 seconds, I would guess, 10, 20 seconds. So it's a noticeable delay, but it's not a huge obstacle like it would be from Mars, where the time delay can be 15, 20 minutes.
Even that's not such a long amount of time from, considering that it's from Mars, I can wait.
Yeah, but it does mean that, the round trip is more like 40 minutes. So it means you can't really control anything remotely on Mars. You have to, if you're sending a rover there, it has to kind of behave on its own because there's no way to respond to challenges on the fly.
And was all the deployment of the telescope that was done by control, like from?
Yeah, it was done by remote control. So Webb is close enough that it doesn't need to be autonomous.
Oh, you don't want to play, huh?
I see a question has come in on the chat. Can you go back to the first picture of the Webb telescope? Let's see. So the very first picture I showed, I guess, was this one. Let me bring that back.
If you hide, if you come really close to Daddy's,
How's that?
you're gonna be.
Oh, no.
Daddy's.
How did you find?
And then the other request I see in the chat is to go back to the purple stars. I can certainly do that. I think that was, let me find it.
I'm in a place where I can't really find it.
Okay, we gotta start counting.
Here we are. So this is that beautiful image of the night sky with stars of different colors.
Inside the bath.
Okay, has anybody else worked up a question? Yes, I see. I don't know your name, but you're wearing interesting glasses with horizontal lines. You'll need to push the mute button so I can hear you, or unmute. Yeah, I see your lips moving, but I don't hear anything, I'm afraid.
If I tell, but I'm trying to help you unmute. There you go.
Okay, go ahead.
Okay, so how long did it take for the telescope to get from Earth to its destination? And what day did it get to its destination?
I think it took about 3 weeks or so. I don't remember exactly, but it was a few weeks, I think, before it reached its, maybe a month before it reached its current orbit. However, it's not working yet routinely. The engineers need a lot more time. The other reason that they made the mirror in segments, they made little hexagons instead of making one big mirror, is that way they can adjust each segment to get it just right. They have to be lined up exactly right in order to reflect the light and focus it onto that secondary mirror. So they're going to be spending months trying to position the mirrors just right and run all kinds of other tests. But we hope that by June, it will start being useful to astronomers who will begin looking at distant galaxies and planets and other kinds of things.
By the way, my name is Daniel.
Daniel? Nice to meet
Yeah.
you. All right, Edward.
Oh, this is an unrelated question, but like, why am I getting DMs from like in this chat by something, but like, why am I getting like random DMs?
That I don't know. I see.
Unrelated by like someone, by someone with like a teal whoever like
If I know the answer, but we will and
whoever
then
like that
these
whoever like that barren person
it's
is.
just that we chat to everybody. That's all.
They're
That's
sending
all.
it to everybody. I don't know
Everybody.
why.
That's okay.
I thought like I saw something like unrelated asking about this plush thing. This is a squishmallow. And I don't know, like.
Yeah, I'm afraid I don't know anything about that. You'll have to have.
But I have a question. Are you planning to do something more with the space knowledge? Since like in the distant future, we probably won't do much with the stuff that we know. So.
Well, I think you're asking what am I interested in doing with telescopes with the Webb, and the answer is I study planets. I try to find new planets around other stars and compare them to the planets we have in the solar system, try to figure out where planets come from, how do they form in the first place, why are they like the way they are, and eventually maybe the next generation or the generation after that might even figure out if those planets are inhabited, if there are any creatures on those planets.
And also Pluto is just a big rock.
That is true. It's a pretty big rock, 1,000 kilometers. All right, any other questions?
What's it like to spend your time like looking at such big and old things, like such a huge scale of space and time?
That's why many of us get into this field in the first place. It's kind of the ultimate perspective altering subject when you have to bend your mind to consider things that are far vaster than we have in our brains are designed to imagine. And at the same time, you also have to understand basic physics, like what is light and what is an electron and all kinds of other things, because that will affect how we interpret what we see out there. So that's one of the most appealing things about the subject. It connects the vast, the distant, the ancient with our basic understanding of physics that we get from experiments on the Earth.
Josh, does anyone have any idea what happened before the Big Bang?
Not really. So I am, as you can guess, I'm not one for wild speculations. I enjoy reading about them, but I don't want to mislead people about them. And the actual evidence for what's going on takes us back to about 2 or 3 seconds after the Big Bang. Where we have a pretty good model that tells us the story of how the universe has developed, starting at around 2 or 3 seconds after some kind of initial singularity. And so we have very direct evidence based on measurements we make with our telescopes. Before that, we have no evidence. All we have is theory to try and guide us, to extrapolate what we know and try to guess what might have happened even earlier. But it will take, and those, a lot of people have very different guesses about that. So it's very unsettled. But there is hope that we will, by building new kinds of telescopes, designing new kinds of experiments, be able to go back even further and figure out what happened in the first nanosecond. And even if it even makes sense to think about what happened before that initial expansion.
Okay, I think Daniel had one more question, and then we'll probably going to say goodnight. Did you have another question? Oh, I can't hear you, Daniel.
Sorry about that.
That's okay.
So this doesn't really include the telescope, but what's the big, round, bright ball in the middle of a galaxy?
Oh, yeah, let me show you a picture. This is a good one. So what you're seeing here, you see this bright object in the middle of the galaxy. That is really the light from billions of stars. So if you were to actually dive in there with a rocket and see what's going on, which of course we can't do, you would just see lots of stars everywhere. It's just that from a great distance, it looks like a glow and a kind of blob of light. In the same way that if you're on an airplane and you're high above some city, it might just look like there's kind of an orange glow. But when you start landing and you get down there, now you can see that it's from individual street lights and car lights and that kind of thing. So it's just lots of stars all blended together.
I just asked another question in the chat, and then we'll probably say goodbye.
Is there a black hole in the middle of galaxies? The answer appears to be yes, that for any galaxy that's about as big as the Milky Way or larger, there's almost always a black hole at its center. We are quite certain about our own galaxy. So the evidence is now pretty overwhelming that there is a black hole in the center of our galaxy. And the evidence is that we can see individual stars whirling around it and there's nothing there. Yes, they are whirling really quickly around an apparently blank spot in the image. And they're whirling at the speeds that one would expect if there's a very massive black hole sitting there. And when we look at other galaxies, we can't be quite as certain, but there is lots of pretty good evidence that black holes exist there too.
Okay, I think that is all the questions. If you want to, oh, there you go. I was going to say, let's stop the share screen so we can all say goodbye to each other. I want to thank you all for coming to Space Havdallah II, and I also want to give a big thank you to Professor Josh Wynn for this great presentation and for taking our questions. So
It's a pleasure. Thanks for being curious about this universe and even the multiverse.
All right. Thank you very much. Shavua Tov. I'm about to end the Zoom. I hope you all have a wonderful week.
Good to see you, John.
Hey, everybody. Good to see you.
Thank you.
Bye.
Space Havdallah.
Bye. Okay.